Hey, check this out. You know those full color LED strips you can buy today? Well, here's a strip of 60 of them that found a happy home in our front yard ornament. So let's get into the details of this little project. Okay, here it is. Got two of these plastic party trays from the dollar store. And what we did was put them together with silicone seal all along the edge to kind of waterproof it, make it one piece. The top piece has a bolt through it with a 1/4-inch nut, washer, and some of that blue tack stuff on each side to seal it up. This will be out in the weather. That only attaches to the top side. Then we run the power wire through, and I think hot glued this to just seal it up. There we go. So this will be hung outside, and this will be the power feed. To get at the electronics, which is just in one Atmel chip here. Hello, turn this way, that way. Okay, there it is. All right. This uses one of those strips with all the LEDs on it, a full strip with the 60 RGB ones, 5 volts. That only takes one signal line out of the AT Tiny 85 chip here. So it was easy to put it just on a board. Let's see, you can kind of see the wiring. No, that's just the back with the thing hot glued there. And see if we can see the connections. Damn, every time I turn this, there we go. Connections. This particular kind of perf board makes a lot of the connections. So there are only a couple jumpers and resistors here. Okay. Now, when we want to program this, we get at it with our proto clip jig here. Goes right in on the clip here, and we've demoed this in other videos. This is already wired up to use the bootloader, and all of our projects use bootloaders in the chips. We do a lot of bare metal programming down to the register level, but we use the Arduino IDE and with the bootloader, because that's the really good trick that Arduino produced. And even in this kind of chip, which is 8K of memory, using half a K for the bootloader is well worth it, rather than having to try to do ISP programming each time, which is just nuts. Yeah, we're not showing the whole construction thing here, you know. Not going to do a whole video on how to drill a hole or chop an onion or whatever they do. Well, I bought some of those 300 LED light strips with the programmable LEDs on there, RGB, red, green, and blue. All run on a part called the WS2812B. So grab yourself a Dramamine, because we're going to be scrolling through this document fairly quickly here. So basically it runs on 5 volts and has one data signal. Now the data signal goes in pin 4 and data comes out pin 2. Other than that, pin 1's 5 volts and pin 3's ground. Now they just string these together for, I guess, as many as you want while your power supply holds up. It all depends on this high-low pulse time. The 0 is a shorter pulse and a 1's a longer pulse, followed by a shorter one, plus a reset so you know when the code sequence is starting. If you look at the numbers here, to send a 0 bit, you put it high for 0.4 microseconds. To send a 1 bit, you put it high for 0.8. Then, for the 0, you go low for 0.85, and for the 1, you go low for 0.45. And the reset is anything more than 50 microseconds. Try 100 to be sure, okay, from my experiments here. Okay, now the trouble with writing code for something like this, when purely in software, is that you got to have some time to take care of other business in software. Things like passing parameters and nesting subroutines and defining stuff and moving it around. So what do? Well, look, this T reset time is defined as 50 microseconds. Is it 50? 50 microseconds. And this whole thing here is hardly a microsecond altogether. So it turns out, through experiment, that only the high time counts. In other words, this high time versus this high time gives you a 2-to-1 window. So even with a self-clocking Arduino chip, you can have no trouble developing these two signals. So what's between this load time and that load time? Well, it's anything you want to do. As long as this load time stays under about 8 or 9 microseconds, you'll stay clear of doing a reset. So basically you've got time to play here after you create your pulses. Now we'll get into the software as to just how that works. Basically you send 24 bits, and after you send 24 bits, the next one, the first 24 bits you have lock into the first chip. After that, the next 24 bits are going to pass through. So the first code you send out, the first 24 bits are for the first one on the string. The second 24 bits are for the second one on the string. This output is not activated until this receives 24 bits. At that time it becomes a pass-through. Well, that makes a system you can just extend as long as you want. Alright, now here's our schematic. Now this is a perfect job for the AT-Tiny 85 if there ever was one, since we have exactly one signal line coming out, driving that LED strip that's so popular today, which all it needs is 5 volts ground and a single data pin. And the software is just all done in here, lots of room for that. The only other component is a 10 microfarad capacitor just to keep the voltage stable. This is actually fed with one of those USB 5 volt adapters, which have like 1 amp output, which is plenty for running the strip. What I have here is 60 LED strip, and we'll get into the software and show you just how this all runs. Here's the software. The first thing we got to know is we're running on the 85 as selected here. This I usually enable. I'm really not sure what it does. This one was at the regular clock frequency. 85 is true. Now this is important. This is running the 16 megahertz clock. Now the settings here, while we're just either viewing or even compiling the program, will not change the clock, but that setting will affect the accuracy of the delay instruction and maybe some other things. So that's important to have those settings when you burn the bootloader into the chip, and you'll see my other videos on burning bootloaders. Now here's the program itself. I got LED set to 60. What I'm using is one of those LED strips with the intelligent RGB LEDs on, and I decided this would be a perfect project for one of those strips because it's got just all those lights with all those colors. Now I'm not going to get into a lot of detail here about all this works, except we're using one line on port B. It's set as an output, and then all this stuff, call these different routines with parameters, runs a cycle through different ones. Now they're all in here. You're welcome to peruse it. I don't really believe in libraries. I'm just giving you the code. You can do what you want with it. Now there's probably some dead code in here because I was experimenting with a lot of variations. But that's not a problem because of the very aggressive compiler, C compiler that Arduino uses. If you, for instance, never called this routine wind up here, it wouldn't even compile it. It just throws it away. And that can be a problem sometimes. I once wrote my own delay routine in C, and the compiler removed the entire thing, I guess figuring that it was just a waste of time. Now here's the critical part here as we scan on down. This function called RGB bit, this is the one that sends one bit out. Now here's the byte command because it sends out 8. And there's another one, the color command, where it sends out all 24. If the bit is a 1, it generates this length of pulse. It sets this, does these no-ops, clears this here. If it's a 0, then it sends just this many out, and that's how this hardware determines the code. It's all just on the high bit. This works out to 0.8 microseconds, so this is 0.4 microseconds. Okay, so there we have it. As usual, you'll find all the technical documentations and such on GitHub with the link below. I found this to be a very interesting project myself. I do a lot of projects like this. It's kind of what I do. So y'all might want to come back here and just check in once in a while to see what I'm up to. Have a nice day.